So data layer, so it's about data placement and repair. Those are the prime things we're going to talk about. And so object data, it's still billions of objects, but now it's storing the object data itself, which is a stream of bytes. And as I mentioned earlier, it can be kilobytes to terabytes. And basically, how will we store that over a fleet of thousands of disks? And the question came earlier, it's about, this data layer really is about dollars per terabyte per year, cost efficiency, not losing your data, durability. I think the number of 9s was mentioned earlier. So that's typically how durability and availability are expressed. So I think depending on the erasure code, you get different durabilities, 15 nines, 20 nines. We'll go into how that affects durability, and how repair and erasure coding make that happen. And then availability is, of course, about uptime of the system. And there, of course, the number of 9s is way lower. I mean, 4 9s is already only 52 minutes of downtime per year. And we just mentioned the HA networking, dual power, all those kind of things. The fact that we need multiple servers, those are all there to ensure that these availability and durability standards can be maintained. And so in the data layer, you want sequential I/O, high performance streaming read and write. Quick primer or erasure encoding. So you take the object here, it's again this MP4 tech field A22 -quantum, and you split it out into multiple chunks, and you add some parity chunks to create extra redundancy. And so this has been around since, I think, the 1960s. Communicating with satellites. This is basically a lot of communication and storage systems use this technology. It's RAID systems are fairly similar. So it's not something new. It's how you apply this Reed-Solomon erasure coding in an object storage system where the special sauce is. And so let's take an 11+4 code, which means that you generate 4 extra redundancy parity parts. So you end up with 15 parts, and you can lose any 4 out of them and still reconstruct your data. And so basically you take the object, you split it out into 11 parts. Those are clear text. You can just read them clear text, and you generate 4 extra parts. And so basically you have 36% overhead, 15 divided by 11. But you can basically lose 4 chunks. So losing 3 chunks is not a problem. You can just read back the chunks which are there and then reconstruct the data. And of course, you want to rewrite the chunks which were missing back to the system again, so you are back at full durability for this object. And so by writing these 15 chunks to 15 different HD devices, on the right side, you see a fleet of HD devices in no particular order. This is, again, just a logical view of the system. This is, we'll go into detail in the next slides about how you can physically lay this out. But by storing this out across 15 different disks, you basically protect against losing 4 disks. And so, as said earlier, this only added 36% overhead, and yet still we can lose 4 disks. If you would store multiple copies of the data, you would need 5 copies of the data to be able to lose 4 disks. And so that would amount to 400% overhead rather than 36%. So this is really, at this scale, all these object stores, all these systems which store petabytes of data, they leverage this technology to be able to have a storage overhead, a low storage overhead, yet still availability, durability, and cost efficiency, of course, because a low overhead means that you need less disks, so you basically can store more data in the system. Of course, disk failure is not the only protection we want to have. So we want to also protect against node failures in this JBOD model, the enclosure or the JBOD failing. Rack failures if you want, and if you place the different racks in different geos, even geo failures. So there's no more than a number of chunks on these. Is basically a hierarchical placement that you want to satisfy. So you say, I don't want to store out of my 15 parts. If I put 2 on the same disk, that's kind of stupid. If the disk fails, I lose both of them. Let's spread them out over disks. And so you can do the same thing. I don't want to put all my parts on the same node, because if that node fails. And so at the bottom, you see an example where there's 3 racks, and you can store basically different. You can say, okay, I want this system uses 2 disks on the far left of node 0 in rack 0, 1 disk node 1 on rack 0, 2 disks in node 2 on rack 1, etc., etc. So for every object in the system, we look at this hierarchy, and so this is really defined by: do I want to have a 3GEO system? Do I want to have a rack resilient system? Those then force you to put at least 1/3 of the data in these 3 racks. So you can lose a rack, and then from the remaining 2 racks, you can recover your data. For 1 rack systems where you don't want that rack resiliency, you have the disk and the node level, which are of course also maintained for the 3GEO system. And so for every object coming to the system, we basically calculate dynamically on the fly. We calculate displacement, and we choose basically based on which disks are up, which nodes are up, what's the load on these nodes and disks at the moment. So we can dynamically choose the best set of disks for this object at this point in time, and keep on dynamically doing that, and that allows us to leverage the entire system. And so,
hey Thomas, what's the size of these chunks? Because if they are rather small, being an HDD, the latency will be high. So I assume that you will be putting large blocks of data on there so that it's at least sequentialized to get a better performance.
If we have time, there's a slide on that.
There's a quick answer, Thomas. We do have small file aggregation capability. So if you have a small file, we actually aggregate multiple small files into a bigger, a bigger file or a bigger object, and erasure coding is then calculated on a bigger object. So when you're dispersing or when you're putting the chunks on the drives, they're consistent. So they're not, they're optimized for what's the best way to write it and for capacity utilization. This dynamic calculation and placement of these chunks across the available drives is unique to ActiveScale, and it also the result and the benefit of it is that we don't actually ever rebuild a drive. So when a drive fails, we actually, I'm going to say we rebuild the endurance level, or bring data back to the endurance level that it's required. And so we identify, for example, what chunks were on the drive. If the drive failed, we identify what chunks were on that drive, and then we seek out additional placement of those chunks to bring that back, the endurance back. But from a small file perspective, we do small file aggregation. Does that answer your question?
Yes, that answers my question. Now, who is doing this? Is that the access layer then, or the data layer? I assume it's the access layer.
So there's both. So the access layer can aggregate small files which are ingested at the same point in time during different connections to the system. That's one way to group objects. We never stage data for instance, on a local device in the access layer to aggregate more data. We don't do that because that's then a different durability and availability model. If that drive would fail, your data would be gone. We always do the full erasure encoding. So if there's sufficient parallelism to the system, sufficient connections, you can aggregate multiple small files from different connections. If that's not the case, then your system is not loaded, and then the data layer can, in the background, find multiple small files and group them together. So in the future, they will be read with sequential I/O, and they will be repaired with sequential I/O.
Okay, thanks.
So it's very important what Noemi mentioned. We do this dynamically on the fly. There's no static link from some systems have the object name defines where the data has to be. And so if that node is down or if that disk is broken, then they have to write it somewhere else to some fallback path. And then when that disk comes back, they have to move the data to the original path. We just, we don't have that. If one of the nodes in node 0 is down, we would just pick another one there. And if node 0 is down, we would just pick node 3. So there's no static link at all. We can dynamically keep on any placement which satisfies this hierarchy of don't put 2 chunks on one node, don't put more than 3 chunks in the erasure code. Sorry, don't put more than 1 chunk on a disk. Don't put more than 3 in a single node. Don't put more than 1/3 on a rack in a rack resilient setup. That's the only thing which needs to be satisfied, and you can pick any device which satisfies that.
This is the reason when I said what is the minimum configuration. This is why we want to have a minimum configuration of, let's say, 3 nodes or 6 nodes in terms of data nodes, in order to assure that we can sustain, multiple drive failures, chassis failure, and of course, if they are distributed across geographies, a whole system failure, right, or a site failure. So this is what is required. So a minimum of 3 nodes, let's say, is required in order to assure that you can lose, a certain number of drives and you have that failure domain still in place.
Yeah. And the same thing holds for the metadata, where we also place that in the same manner that it's across these nodes. So if you lose a node, that you can still have 2 of the 3 nodes running the majority system, and the system is still live.
I have a question about data placement in terms of tiering. Is there some sort of tiering functionality supported? Something like infrequent access on S3, or moving something off to even lower cost storage, kind of like Glacier, but maybe not on tape?
So you're jumping ahead. That's a future. And okay. So if you want to talk to us later in 2021, we can share more on that. But yes, okay. It's actually in the works.
And so now that we've stored our data across this fleet of devices, of course, over time, disks will fail. I mean, hard disks fail with a failure rate of a couple of percentage points per year. I think in these JBOD models, we see a bit more stability, but still, disk failure rates are not in our control, but repair times are. And so an object storage system should really double down on repairing the data as fast as possible. And definitely, we don't wait for the human intervention. We don't wait for somebody to go into a data center and replace a disk. So in this example here, there are 3 objects, each having these 15 chunks. So they can each survive 4 failures in the 11+4 code. So there's a blue, an orange, and a yellow object. And we have picked 4 failed devices. And so the top left, that had a chunk for each of the 3 objects, and then the other ones, the other disks only had a chunk for one of the objects. And so when this happens, we repair data. We don't repair disks. So it's not a RAID system, because with 18 terabyte drives and a RAID, the disks haven't gotten any faster. They've only gotten bigger. So repairing a single drive to another single drive, that's extremely slow, especially when these drives are still, the drives in the RAID set would be serving reads, customer data, and other writes. So that's just not feasible anymore with these large, with the current drive to throughput numbers. Instead, we use all the disks in the system to together repair the data. So we leverage, and that's again where this dynamic data placement is great, because we can find new combinations that are perfectly fine, rewrite the missing chunk there, and we can leverage the throughput of all the spindles together to repair the data and not repair disks. The disks are broken, we don't care about them anymore. They basically are expunged from the system, and we repair the data. So if you look at this example, the orange object is in trouble because that actually has lost 4 chunks. So it's basically at safety 0. One more disk failure would basically cause the system to lose that object. So ActiveScale has a priority-based repair feature where we first repair the orange object. And so the system has a way of identifying if these disks have failed, this is the list of affected objects, and they are ordered then in terms of severity in case of multiple disk failures. And so there's an order of magnitude less objects that are have 2 failures and that have 1 failure, and then again an order of magnitude less that have 4 failures. So by repairing that most affected objects, you really very fast alleviate the true durability problem, and you're back to safety extremely quickly again. So basically, the only thing you need to do is repair this handful of objects which are critically affected.
I've got a non-technical question for you.
Yeah.
Who do you see as your primary competitors for this solution, number one? And then I've got a follow-on question after that.
So the main competitors are the other object store vendors.
Well,
but I mean, I don't know if
are you going after on-premises solutions, or are you looking at more of the cloud solutions?
So this is a private cloud solution. You can deploy it on-prem for the most part. We do have some adjacent technologies and products that can facilitate movement of data between, let's say, on-prem and the cloud, and give you some insights and real data management capabilities. But this is an on-prem private cloud solution.
Okay. The reason I asked that question is because in conversations with customers of very large insurance companies and financial institutions, the CTO said, 5 years ago, 80% of our data was on premises and 20% was geographically dispersed in the cloud or other data centers. And I foresee in the next 3 to 5 years that 20% of our data will be on premises and 80% will be in the public cloud. Is there do you have a roadmap or a direction to take this from the private cloud into the public cloud?
Well, so the first thing I would say is there are specific use cases and reasons and requirements for why would you go to a cloud, public cloud, or why would you stay in an on-prem private cloud? And I think that it's been a very long time when people have been saying it's like, oh, cloud. But today, the economics of cloud is such that if you're storing cold data, in other words, it's your expectation of accessing the data is pretty much non-existent. So it's an insurance policy. Then you could arguably say that putting it into something like Glacier or cold storage, Blob, is effective. You're paying less than a penny per gig per month, and over time that works. Now, as soon as you start saying that, this data, it's a unique instance of the data, but I need to access it, I need to share it, I might do analytics on it. At this point, it becomes a little more expensive to keep it in the cloud, and you would do an analysis in terms of what is financially more feasible. And I think that in speaking to many customers and working with customers over the years, many of them have had the directive to go to the cloud, have gone to the cloud in terms of assessing, what do I get for the service? How much is it going to cost me? What are my budgets? And have opted to actually stay on-prem. I'm not saying that everyone will. There are definitely use cases, iterative use cases, project-based initiative where you don't want to invest in resources for a short period of time. That cloud makes absolute sense. And we're definitely, as a company, are developing and moving our products in such a way that they can interact with public cloud and enable our customers to burst or to move data back and forth as necessary. But I don't think that it's all said and done. Everything goes to the cloud, or.
Right. No, I agree. No, it's not said and done. Everything's going to the cloud, but that makes a lot of sense what you just said. So really, what you're seeing is, and I'm putting words in your mouth. So let me know if I'm saying this right. But what Quantum is saying is, Quantum is going to be the repository for that 20% of data as that data starts to kind of trail off. Sorry, I didn't mean to say failure. I saw those red X's and I went to failure. But to trail off from the on-premises data center, you're seeing that Quantum is going to be that storage repository for that 20% ultimately in 3 to 5 years.
So one correction to that, I don't believe that 20% is what's going to be on-prem and 80% is going to be in the cloud.
Okay.
So if we take the assumption out of the calculation or the statement
Sure.
and say that Quantum is positioning ourselves and delivering solutions to be the de facto leader in storing unstructured content and unstructured data. Now, we're also, like I said, delivering solutions that enable you to collaboratively, interactively work with resources in the cloud. So it's not like all on-prem or all in the cloud, but we're going to deliver, and we are delivering solutions that are very cost effective and that have enormous amounts of features that organizations seek in terms of security, which we didn't get to, with our encryption at rest, encryption in flight, object locking capabilities, full immutability, which is a function. I mean, it's an inherent function of object stores to be immutable, but we're going one step further and saying, hey, you can define whole buckets or objects that can be immutable, and nobody can change that, meaning you can't maybe move it, you can't delete it, you can't read it, you can't do anything with it, and it can be protected against ransomware, but it also be compliant with many retention requirements. So there's a lot of features, there's a lot of capabilities, and we're definitely working and driving the costs down. And as I think it was Ned who asked about, tiering. So, and we'll be adding additional functionality to further enable customers to store data in the most, cost-effective way without compromise on durability, without compromise on accessibility and availability of data over time.
Excellent. Yeah, you mentioned something, data management, early on in your response, and I think that's really the big thing. I think that Quantum brings to the market is that data management component. So I'm going to be very, very interested to see those other announcements, those other things you have to talk about from that data management perspective.
Yes. So we'll have another session going with Tech Field Day probably in another 6 to 7 months next time, where we will talk about that. But in terms of data management, if you look at the announcements we had made back in November, we have brought to market a product called ATFS, which is a NAS with NFS SMB access and ability to move data in and out of object stores. So what it does is an inline ingest at ingest time. It tags data, it captures metadata, and enables you in real time to really understand your data. And so now you can use that with API integration to manage what goes into object, what comes out of object. And again, object on-prem, object in the cloud, really doesn't matter. It's all about data control and visibility.
Thank you. Excellent.
Thomas?
Yeah, so okay, I'm unmuted. So we repaired the orange object, and then of course we need to repair the other objects. And so yellow and blue also, the missing chunks get rewritten to other disks. And you can see that on the top left we had these disks which had a chunk for each of the 3 objects. And so these 3 chunks didn't go to one single disk. Again, this system has a dynamic data placement. There's not one static disk which replaces this other disk. So multiple spindles participate in repairing the missing data. And that greatly improves the repair speed. And that, of course, is what crucially defines the durability of the system. So that's how you get to a lot of 9s. And then a couple of months later, someone goes to the data center and they replace the missing disks and add brand new ones, and those get leveraged by the system again. And so this is basically just freeing up that capacity again. So if the disks are broken, of course, you lose some capacity. And then a couple of months later, you add the disks and then you regain that capacity. So you only basically do that if that's required, or on every couple of months, you go to the data center and replace a broken disk. So replacing disks is not part of restoring data durability. There's no human in the loop. And so we want to scale out the data layer as independent pods. These systems of dynamic data placement and dynamic data repair, as you grow the system, they have diminishing returns. And so you don't want to scale these pods bigger than necessary. If you look at the X100 example we had before, if you don't want rack resilience, there's no reason to scale your data pod larger than that one rack, because if you do that, you get cross-rack traffic. And so by keeping the pod within one rack, you can more efficiently leverage the network infrastructure which is in place there. And so, of course, if you want rack resilience or if you want 3GEO, then you would have to have a 3-rack pod. In 3GEO, have these 3 racks in 3 different geographies connected in the WAN or a metro network. But the prime difference with other systems is that they have also the data layer and the metadata layer scaling are hard tied together. And so they grow the data system together when they also scale the system. And that requires rebalancing the data between these different racks. And that basically causes petabytes and petabytes of data to get rewritten internally in the system. And that causes background load on the system, which is basically not necessary with our technology. You don't need to do that. So by adding racks as independent pods and having a unifying metadata and access system on top, you can prevent that from happening. In the background, there's background scans going on, looking for bit rot on the disks, reclaiming space for deleted objects in the background, minimizing the I/O in a throttled fashion so we don't affect the foreground operations. This is the use devices in the optimal way thing we mentioned this. So object aggregation, there was a question there. So you group small objects together and then put them in the data layer and erasure encode them. That allows you to leverage disk throughput and not disk IOPS, because there's a lot of throughput in a disk, not a lot of IOPS. And so when these objects are grouped together, you can read them back with a single IOP from a single disk. And you can also repair the entire thing as a whole, which is way faster than repairing a lot of individual small objects. And it also has the same durability, availability, and storage overhead as any other object in the system. So this is coming up in our next release.
My question is, it's probably more of a general question, and I don't know if it's been really investigated so far, is what are the key use cases that you see for this technology on premises? I know generally how object store is used in a cloud context. Are you assuming it's going to be the same type of applications that are just happen to be running on-prem? And if you have some actual one or two customer examples at scale, that would be really useful to sort of hammer home the point.
So the use cases on-prem are, some of them are similar. So you can run any application that runs across S3, whether it's Spark or Hadoop applications. Object stores are also commonly deployed in active archive implementations. So I need to preserve data that is unique instanced data in organizations that have a lot of unstructured data, media, entertainment, life sciences, pharmaceuticals, engineering. This is data that may not be frequently accessed. It's not changed. That specifically. Video and streaming data is commonly, because it has good streaming performance, you can do on-prem. Like I said, it is very secure system. So for a lot of organizations, they don't want to move their data into the cloud. There's concerns about storing data in the cloud. Whether those concerns are real or not is a separate conversation. But there's so these are the many sort of use cases. It's a central repository. If you think about it, is a big bucket where you can put lots and lots of data, and then you can use lots of different applications or front ends to give it a different personality. So I can put my StoreNext file system, which is a high throughput, low latency file system, and I can store inactive data in ActiveScale, which is going to be highly resilient, very much available, lower cost, and only move it into the file system for when I need to actually do something to it and leverage that. I can also put my ATFS, which is going to give me all the information about it, so I can actually data manage my data. And again, I can move it in and out of ActiveScale to ensure that it is, safeguarded at, the trade-off. Not a trade-off, but that the data is preserved and is going to retain availability at an appropriate cost or appropriate, delivering the value that it has. So there's lots of different personalities. It's not just the applications that might be used in the cloud, though those you can use them on-prem as well, and many people do.
Right. Do you have like a customer example that you commonly bring up that shows how it's being used on premises?
I mean, I have a university customer. They do life sciences, HPC center research. And actually, they have an object store deployed across 3 sites. They ingest data in one location, but they use the 3-site dispersal for site failure, resiliency, et cetera. It stores basically all of their research data. All the results. Anything that's archived or has retention requirements gets stored in the object store. So there's different interfaces to it. We also have media entertainment customers who store all of their, initial video assets in an object store before or after they need to, process it. So we have a number of customers. We can give examples. I think that the easiest way for me to give you like the full information without taking time from a demo that we want to do is to, if you go to our website, we have a number of case studies published around ActiveScale and across a number of different industries. So, we have customers with 100 petabytes.
That is significant.
That's some storage. So I think the only thing I would want to add to that was that in some of these use cases, I think we have a genomics reference customer there as well on the website. So in these use cases, they're writing and reading multiple gigabytes per second per rack to these systems. So if your data is generated on-prem and you want to put it in the cloud, that's a very hefty transfer rate. And so for these customers, it's more economical to also put the storage system on-prem and leverage really the high throughput of the system to do a lot of data processing, read the data back and do genome analysis and research on it.
A lot of the times, the most expensive part of data in the cloud is getting it out because the network transfer fees are, well, they're not kind to any of us.
Yes.
Is there something on the roadmap to assist with extracting data from an existing S3 onto on-prem, if that's the way you want to go, in a way that is less cost intensive?
Well, the cheapest way is to, get a direct connect or one of those direct connect network links. I mean, you might pay a fortune for it, and then you would download all your data. But realistically, there really isn't a way that you can extract the data out of the cloud without paying the egress costs. I mean, that's just the one thing that I think you could benefit from is then implementing a data management system that would actually allow you to understand what you have in that bucket so that it doesn't become a black hole. And then once you actually go through, and this is why we're really big on data management tied to storage management, because a lot of times you just dump data and then you don't really know what it means, what the liabilities of having it or not having it are. And so you just keep it indefinitely and you end up paying costs for it. So before you would actually extract data from the cloud, I would say make sure you have a data management system in place to actually ascertain what data is there and what data represents value. And if it doesn't represent value, just delete it.